continue with the force and motion stuff, which is, still, this is all in your book, okay? Um, and we're going to talk about springs. All right. So last week we talked about Newton's laws. We talked about Newton's first law, right? Saying that Newton's first law says that the sum of the forces are equal to zero, then your acceleration is zero. So if you're falling, out of the airplane, once you hit that terminal velocity, you stay at that speed until something changes. That's what we were just talking about in that. So, or if you're sitting here, listening to the lecture or whatever, you're not moving because your forces, all the forces are at rest, acting on this body. So, but Newton's second law says then that if you have an outside force, or if the forces change somehow, then that mass is going to accelerate, right? And the acceleration is due to the unbalanced forces, okay? So if the forces are balanced, then you're not going to move. But if the forces are unbalanced, then you get this reacting force, which is based on your acceleration, so that the body can speed up or slow down based on, because the force is acting on it, there's a difference in them. So his third law says that for every action there's an equal and opposite reaction. And so that's basically what this equation is saying, is the fact that, okay, well, if the forces aren't equal, then there's an acceleration force. And so this is the acceleration force. And so we can then therefore calculate that the acceleration with respect to time is equal to the force divided by the mass. Oh, well, that was supposed to be over top of the other one. But so we've got that. But now we talked about friction. We talked about friction and how friction is dependent on the velocity. So friction is a force, and the frictional forces applied to a body that is in motion is proportional to the velocity. Okay, so it's we had Newton's law of Newton's friction is actually his is based on velocity squared. Stokes is a different approximation, which is just on velocity, not velocity squared. But it's the key point here is that the force changes based on the speed of the body, the velocity of the body. All right. And then now this is something new today. Then this is Hooke's law, and Hooke's law is about springs. And so if you have a spring and you compress that spring, Hooke's law says that that spring is going to try to push it back out. Or if you stretch the spring, it's going to try to pull itself back together again. And so that force is opposing the direction. If it's compressed, the force is pushing in the opposite direction, trying to spread it back out. If it's stretched, then the force is trying to pull itself back together again. So, this is the property of a spring, and this is, what they call Hooke's law. Okay. And so Hooke's law is due to the position, the first order, right? X. X here is the position. Stokes' law was due to the velocity, but Hooke's law is due to the position of the thing, and it's a restoring force, so it's always going in the opposite direction. Okay, and this is a linear equation, so this is assuming a linear response. In reality, this only occurs for small compression or stretching. If you get too far out of here, then you get this curve going here. Okay, so if you get over here so far that you stretch that string too far, and then you just basically destroy the spring. It doesn't work anymore, right? So if you ever, like, I don't know if you ever had like a slinky or something like that, and you know gave it, your little brother or sister got a hold of it and just yanked on it, then it's out of what, it's parts of it gets bent and it doesn't work properly. So if you get over here, then you're basically distorting the spring. But if you stay right here so you don't stretch it too far, then you get this nice linear response, which is Hooke's law. Okay, so Hooke's law only applies assuming you didn't bend the spring out of its thing. So it's got to be within a certain amount there. All right. So, but what this now gives us is if we take I thought I had a drawing of this. I guess I don't see a drawing of this. Usually I draw on the board, but since this is an online class, I guess I'll have to draw here. All right. So if we take this, this is just a thing here. What we're going to do is we're going to take a spring. So this is my spring here. And then I'm going to attach a mass to this spring. Oh, that's tiny. Wait for my mouse to catch up with me here. Okay, so this is our spring. And this is our mass. And so what happens is when we attach this mass, when we attach the mass to the spring, gravity is going to pull this thing down. So we're going to start out here. We're going to start out, this was like the normal stretch of the string. But when we attach the mass, it's going to bring this thing down here, and the mass is going to hang down here further because we put more tension on it. Okay, so after we color here. All right, so this is where the spring was at. But then when we attach the mass, this thing's going to drop further down. And so this distance here, okay, the distance here, if this isn't bouncing up and down, The distance is when the weight, the force due to the mass, right? The force due to the mass times gravity is equal to the spring constant K, call it Ks, the spring constant Ks times the distance x naught, where this is that distance. Okay, so the distance that this thing hangs down, okay, the distance that this thing hangs down is actually then the mass, the amount of weight, of that thing times gravity divided by the spring constant. So we can tell how far this thing is going to stretch by just, by using this equation here. So we're using, Newton's law here, which is saying that the force pulling this mass down is the mass times gravity. That's, gravity is the acceleration. So the force pulling down here, gravity is pulling this thing down, and the spring is trying to push it back up. So the spring is trying to push it back up. And if these two are equal, if the magnitude of them anyhow is equal, if the absolute value of these are equal, one's pulling up, one's pulling down, but if the absolute value is equal, that'll give us the distance that this thing is going to sit there at, okay, using Hooke's law. All right, so this, remember this bit over here, this is Hooke's law here. All right, so now the acceleration, okay, the acceleration is equal to minus, because remember the spring is always operating in the opposite direction. So it's minus K, which is the spring constant, Ks, the spring constant, times the deflection, how the position. X is simply the position. The x double dot is the acceleration, right? I talked about that in last week a little bit. I introduced the notation of x double dot is a notation for the time derivative of a function or a system. So x is the position of the mass. X double dot is the acceleration of the mass. Now, and then this F piece here, this F over here is a forcing function, which I also talked a little bit about forcing functions before. The forcing function can be applied to drive the system, okay? Or it could be zero. All right. So to get the system to move, remember Newton's first law. Newton's first law says that the system isn't going to do anything unless you have an external force, right? So if the system is sitting there doing nothing, it's going to stay that way. That's Newton's first law. So we need some kind of something to get the system to move. So we have two ways of doing that in our simulation. We can set an initial condition, or we can apply a forcing function, or we can do both, okay, if you want. But so how do we do a initial condition? Well, if we look at this, right, this x0 value here is its default point. So if the system is just sitting there hanging in this spring, it's not moving. There's nothing to move it. So what we could do is we could pull the mass down. We can pull the mass down here and stretch it and then let go of it. So we could give it this this new X at the beginning of the simulation. We could pull it down this far, and that'll be the initial condition. And then we let go of it, and it's going to bounce up and down, up and down, up and down until it settles back down to where it started at. Okay, so here's the system. It's just sitting there. It's not moving. It's just sitting right here. It's not moving. And then we grab a hold of it and we pull it down. We pull it down here and then we let go of it. Now it's going to bounce up and down and up and down. Now, theoretically, okay, theoretically, this thing's going to bounce and run forever and will never, ever stop. All right. And that gives us this plot, which is called just, well, a harmonic motion, but it just is going to bounce up and down and will never stop. There's nothing in this equation. Where'd that equation go? There's nothing in this equation that is going to stop the spring. Okay? It's just going to sit there and bounce back and forth forever. However, in reality, we know that there's friction, right? So we know we have friction. So in this equation, we're ignoring the friction. There's no velocity term here. There's no friction. Okay. So if we add in the friction, I don't know if I gave you that. I'll come back to those other slides there. But if we add in the friction, here it is. Okay. If we add in the friction now, here's my velocity term. This is Stokes friction. And notice the negative sign there. Okay. This is going to oppose the acceleration because friction is always operating in the opposite direction of the acceleration. And so if you're accelerating down, friction's going to try to slow you down, you know, and push against you going downwards. But then the spring is going to start pulling you back up. And when the spring is pulling you back up, friction is trying to slow you down again. Okay? And so it's going to try to keep you from going back up. Friction is always running, opposing you. And so now we get an oscillation like this, which is a damped oscillation. So it starts out and you have some pretty big oscillations, and then the oscillations get slower and slower. All right, and that's what you'll get from this equation right here. You have this is the equation for acceleration, right? X double dot is acceleration. Here's your equation. You have a spring constant, and then you have a friction constant, and then you may or may not have a forcing function. Okay, so let's talk about these forcing functions. There's several different types of forcing functions that are available. That we tend to use. I mean, theoretically, you could use any sort of function to push the system. All right, but the most common that we use in simulations are right here. The first one is called the Dirac delta function. This is just like when you bump it. Okay, so when you just push it and let it go. So kind of like what I was talking about here, I said we could grab a hold of the mass, pull it down, and then let it go, and then we don't touch it anymore, and we just let, physics do its thing. So that would be the Dirac delta function effectively. So the initial condition, we press it, and then we do nothing else. All right, so then the other, another choice is a constant force being applied. And so a stepping function is what we refer to it as a unit step, which means that we're going to just constantly push it. One example of thinking about this would be something like a rocket. If you think about trying to launch a rocket, you ignite the rocket propellant, and the force pushes constantly against that, right? That rocket, is spewing out the exhaust there, and that's constantly pushing you until you run out of fuel, of course. But it's a constant thing. So it's constantly acting upon it. All right. So how do we do this in the software? Well, it's really easy. We already have T, right? We have already created T equal to 0 colon some kind of time step to something, right? To some value, 150 or whatever, 250. All right. So we already have T. So now what we do is we can create our forcing function. Usually we use the symbol U a lot of times as our forcing function, or you could use F, I guess, if you wanted. But this would be 1's size of T. And so you would just get 1's in there, and you would have that in there all the time. And then if you wanted to scale it, you could say, well, this is, 2.782 or 3 times that, and this would scale it. So without that, it's just what we call a unit function because it's 1. So it's 1 times whatever. So it's a unit force. But you can scale it, just multiply or divide it by something, and you can scale that. And that would be your forcing function of a step. Another choice we could apply something like a sine wave to it. And this would drive it in a smooth back and forth sort of driving motion. So we could push it. So, you're just constantly applying pressure back and forth and back and forth. So these are, like I say, there's lots, theoretically, there's an infinite amount of type of forcing functions that you could use, but these are 3 that is very commonly in the soft for simulations. Okay. All right. So, one of the things that we're going to do for the homework is we're going to model a bungee jump. Okay. So I don't know if you've ever went bungee jumping before. I think I actually have a video link somewhere of some people going bungee jumping. It's not something that I've ever done. Maybe if when I was younger, I might have considered it, but I'm not going to go do it now, that's for sure. But anyhow, so we're going to have a bungee jump. And sorry. So the idea with a bungee jump, though, is you have the bungee strap, the bungee cord is a spring. It's kind of like a spring, but the problem is that when you go down, it pulls you back up. But after you get to this point, where's it at here? Right here. Okay. After, if you're bungee jumping, when you come back up here, after you cross this point right here where the normal stretch of the rope is not doesn't have any tension in it anymore. Okay, so you're flying up here and you're coming up, but there's nothing pushing you down other than gravity. The spring itself is not pushing you down. And so when you cross this point right here, when you cross this line like that, then the Hooke's law basically stops to applying, right? So this is the restoring force of the spring or the bungee rope. And when you're up above that point, the restoring force goes to zero because it's just a rope and the rope gets slack in it. And so again, you have to use this if statement to control your restoring spring force for the bungee jump. All right. And so as right out of the book here, they talk about this bungee jumping. And, so they're doing a plot here. Now, notice in this plot, they have velocity and the length or the position both on the same plot. But also notice the scale is different. All right. So right here we've got a value of 200, which is the length. But here we've got a velocity number, and the numbers aren't anywhere near the same. So you actually have to scale. To put this on a plot, you have to kind of scale it so that they both look fairly reasonable. So you actually have to add some scaling there. All right, and that's really easy to do. You can do that in the plot. Okay, so if you do a plot and you plot like t comma x, which is your position, and we'll make that blue or whatever, and then you're going to plot t comma your velocity, and you may want to make that red. I don't know if I assigned you colors for it in there, but the problem here is the fact that these aren't in the same scale. So what you might have to do is multiply or divide. So you may have to use something like 2 times your velocity, or maybe you need to have velocity divided by 2. Okay, or something along that way. So that's how you scale it and get them on the same graph. Okay, so it's really easy to do, but the only other catch is that when you put in your legend, when you label these and you do your legend, then you have to have, the first one's going to be your position. That's no problem. But the second one, you need to tell us what the scaling on it was. Velocity divided by 2, or 2 times velocity, or whatever your scaling was for that other term. Okay, so you have to just document that in your legend. All right, and then and since now remember that the units of position would be meters. Okay, so that would be in meters, and the units of velocity would be most likely meters per second. Okay, so you need to document that also. And then in your label, then when you do your Y label, just call it amplitude. You don't put the units there, you put them in the legend, because there's 2 different units here. All right, now on this graph that he had in the book, he didn't even bother labeling them. All right, which is I don't know if it just whatever software he used to do that, or what, but it just, you know, it's not a very complete graph because it's missing any kind of labels there. All right. But I think a lot of his graphs were kind of like that. So maybe he just didn't want to give away the answers. I don't know what his thing was. But the you have this, when you plot it, you can scale it really easy. Okay. Now, notice here, I mean, he's got this number 43 over here. I'm not sure where he came up with that. Okay. Like, I would, if you look at this, right, the top one here is a 200, and this one's 43. I don't know what the scaling of that is. I would simply divide it by 4, right? And that would give you a height of 50, which would make the black plot a little bit smaller than what we're looking at. But I like to divide or multiply by nice even numbers. All right. So I would just do something more like, divide by 4 or 3 or 2. Pick a nice round integer value to either divide by or multiply by, unless you have a really good reason to use some kind of crazy fractional value like 43. I don't know why he chose that scaling, but I do not recommend it unless, like I say, unless you have a good justification why you might want to do it. But in general, I would recommend that you choose nice round numbers like 2, 3, 4, 5, 10, 20, something along those lines. And the plots won't be exactly the same height, but they'll be visible. You pick the numbers so that they're visible. They don't have to reach the same peak. I mean, they don't even on this graph. So I don't know why he chose to make that 43. I would have made it 50 by dividing your velocity by 4 or multiplying it by 4. Or whatever that you needed to do to get it on par to plot it on the same graph. Okay, and I'm pretty sure I did that in a previous video also. All right, so remember, when we do this, we basically, we're going to initialize our variables, right? So you always, right, you're going to have your time step. And if I tell you a time step, you better be using it because your numbers will be off if you don't use my assigned time step. If I don't specify it, then you just need to pick a time step to give us nice smooth graph. If you start getting errors that are something like out of bounds or NaN or something like that, then your time step is most likely too large. And then you're going to create your time variable. So you're going to initialize your time, 0 : time step to whatever the end of time is, whether it's 150 seconds or whatever you need. And you may have to vary this, right? So you run this and then, kind of pick a small number. Don't make it too big. And run the simulation, and if it doesn't seem like it's settled down or whatever, then you expand it, increase your time a little bit. And then of course you have to like initialize x is equal to 0 or x is equal to 1.5 or whatever. So you have to initialize your variables, whatever it is. And then you go into your for loop. Inside of your for loop, k to the length of t, right? So your for loop always looks like this. And then you have your end for. Hey, this software keeps wanting to capitalize it on me, right? And then you're going to calculate acceleration. Your acceleration is equal to your, whatever your equation is. So you have like your spring constant minus your spring constant times x k minus 1. Why did it? That's why you don't use something like Microsoft Word to write these programs. Why is that striking out? And then you have, let's say that's minus, it's minus the time constant or spring constant, and it's minus the velocity or the friction constant times your velocity of k minus 1. All right, so there's your acceleration, and then you just integrate. So your velocity at this point in the simulation, k, is the velocity at the previous iteration plus your time step times the velocity or times the acceleration. Okay. Now, in this case, I'm not saving the acceleration. Acceleration is a scalar. All right. You can save it if you want. You can put it in a vector also if you want. And then we're going to calculate our position, which I guess I just called x. And we're going to integrate x. X is simply the previous x plus time step times the velocity. And that's it. I mean, we do this every single time. So we integrate, we evaluate the derivative, then we integrate. Okay. This so far in this class, I mean, we've been doing this for like 4 or 5 weeks at least now. It's exact same sort of setup. Okay. So you set your t, you set your time step, you build your t vector, you initialize any and all variables, you have your for loop, k equals 2, the length of your time vector, and then you evaluate your derivatives, and then you integrate. And then, of course, after that, you plot. All right, so that's pretty much it for this week's assignment. You have any questions there?